Okay. Hi, it's my pleasure today to introduce Ofer Firstenberg, who's going to give today's colloquium. Ofer did his undergrad at Hebrew University. He was part of the Talpiot program. And he then did his master's and PhD at the Technion. He worked, so his PhD research, he did it in Rafael with under the supervision of Amir Amron and together with Nir Davidson from the Weizmann Institute. And then he went to um, postdoc. You were in the Michel Lukin's group, yeah,
Yes.
at Harvard, and he came back to Weizmann, where he's now a faculty, and he's won recently the Creel Prize of the Wolf Foundation. And today he's going to tell us about some of the research he's been doing, bringing noble gas spins into the light. So.
Thank you, Daniel. Thanks for inviting me. Hi, everyone. Let me start by asking you to stop me with questions during the talk if you want them. This will be much more fun like that. The talk is going to be about spins of atomic gases, in particular noble gases. I'll tell you about our journey in the last few years to realize an efficient interface between light and those spins of noble gases. So the field of quantum optics with atomic gases obviously starts with these alkali atoms. These are surely the all-time main actors in the game. If you don't remember, these are the atoms you would find on the, do you see my cursor? You don't, right?
Sorry?
Here you go, all right. So if you look at the left column of the periodic table, you find those alkali atoms. They have one electron in the outer shell. This electron has a spin 1.5. These alkali atoms can have other spins. So they also have, the electron would have an orbital spin, L, and also a nuclear spin, I. So for potassium and rubidium, the spin could be 3.5, for example. And then there is a total spin, F, that could be 1 or 2. And we play around with those spins, and these spins turned out to be very useful. Now, they are useful partially because they couple efficiently to light, as we will discuss, and partially because they are very long-lived. And it could have lifetimes from milliseconds and even more. And even when they are enclosed in those glass cells in room temperature, and we do nothing special to them. Therefore, one thing we do with them, we build sensors with them. And turns out that they are very good sensors. For example, here is a magnetometer. You see it's a small magnetometer, a few millimeters wide. It has some alkali in it, maybe rubidium atoms. And the reason these are very good magnetometers is because they are very sensitive to magnetic fields. The gyromagnetic ratio of the electron is large. And so in a weak magnetic field, they make many precession periods within the lifetime. Okay, so yeah, you can think about them as very good oscillators and therefore very good sensors. In fact, when we build those magnetometers, they turn out to be among the most sensitive magnetometers that we know how to build. They are also sensitive to electric fields, some of these electronic states. So they can be built, we can build very sensitive electric field sensors from terahertz to DC fields, microwave, RF. They are sensitive to the environment, to the gas composition. So people build sensors for gas composition with them. But in addition to all of those transitions that are sensitive to the external environment, there are also atomic transitions that are insensitive to the environment. For example, those that pertain to the interaction of the electron with the nucleus, the hyperfine interaction. And these hyperfine transitions are actually very insensitive to the external factors, and we can build clocks out of them. So here is another application that is miniature, small, it works at room temperature, even above, and it's a very good compact clock. These two applications and many more are, of course, classical applications. Okay, But we can also do quantum optics with those spins. And let me give you the most simple quantum descriptions for these spins. So it looks like that. You think about a quantum operator S, which is the collective spin, simply the total spins of all those atoms. So you sum over all the spins of all the atoms. You just simply sum over, if they're all pumped up, you will get just a big vector pointing up. And this is the collective spin. Now, a classical state would have all of those atoms pointing up and some uncertainty disk that is due to the fact that these atoms are not correlated and they have a basic fundamental quantum uncertainty. And this is represented by this disk in here. How will a quantum non-classical state look like? So here is one example. This is a squeeze state. The uncertainty disk is squeezed. And the way to get to that is we need the atoms to somehow agree to be together more uncertain in one direction on the expense of being less uncertain or more certain in the other direction. Okay, so this agreement between the atoms, those correlations are the non-classical correlations I'm talking about, and this is one type of non-classical state that we work a lot with. Here is another type of non-classical state. This is a Fock state. This is a state with a definite specific number of excitations. For example, let's say all the atoms point up, and we flip one spin to point down, exactly one, not more and not less. And this generates this type of uncertainty distribution. It's a ring. And here again, there are strong correlations between the atoms, because if I find this one and only spin that points down, I know that all the other point up. So it represents again some correlation that is shared among all atoms. So fine, now we have our non-classical spin. How do we interact with it? How do we generate it? And how do we measure it? Well, we use light to do that. And here is one of the most common processes. It is a Raman process in which we shine light to excite an electron from one orbit, maybe the outer shell, to another excited orbital. So we go from, say, angular momentum 0 to angular momentum 1. And then we go down with maybe another laser field. And in the process, we flip a spin. So here we use light to flip a spin. And the reason we can do that is because there is a strong spin-orbit coupling between the orbit and the spin in the atom, and strong spin-orbit coupling together with very strong optical transitions generate a very efficient interface between light and spins in these atoms. These are standard lasers, visible, infrared, and very easy to generate. And due to all of these very nice properties, quantum optics in the last 20 years was somehow kind of frontiered by these type of systems. Let me show you a few very recent examples for quantum optics with vapor. So I like these two examples recently because first they are very recent from this year, this Corona year. They come from the same group, both from Copenhagen, from the group of Eugene Polzik, one of our main collaborators. And they pertain to these two different non-classical states. So what you see on the left is a vapor containing alkali spins, and we shine light onto them until we see a click coming on this single photon detector. And when we see this click, we know that there is one spin that is flipped in the vapor. So we know that there is a Fock state generated, and then we can shine again another control laser onto this atom and read out this spin and get it in the other detector. So this is a single photon source that is also a quantum memory and survives for a millisecond. What you see on the other side is basically the same atomic system, but here we use light to couple these spins to a macroscopic membrane, a classical harmonic oscillator that behaves non-classically. And what the light does is mediating correlations between these two. And it puts them into an entangled state, specifically a two-mode squeeze state that generates non-classical correlations between these spins and the membrane. All right, perfect. So this is where these alkali atoms stand right now. We now move to the right column of the periodic table, to our modest friends, the noble gases. So of course, here I refer to odd isotopes of noble gases, atoms that have odd number of nucleons in their nuclei such that they have a non-zero nuclear spin. This is, for example, the spin 1/2 for helium-3. Xenon 129 or other isotopes of xenon have non-zero spins 1/2 and 3/2. There is neon 21 that people work with. And these turned out to be also extraordinary systems because they have very, very long lifetimes when you put them in such glass cells. And let me show you some data. These are measurements for different systems done by NIST for helium-3. And you see here that this polarization of the nuclear can survive for many days, even 4 months at the record. And again, this is above room temperature. You see on the right data from our lab, where we measure the coherence time, the precession of the spins of helium-3 around a magnetic field. And you see a coherence time, a T2 time of 2 hours. So precession that we monitor once every 30 minutes and see its decay. So these are fantastic spins. Why don't we do quantum optics with them? Well, of course, because they don't couple to light. By the way, you might think they are exotic and no one does anything with them, but they are not exotic at all. There are applications. Here are two. This is an imaging of the lungs done with hyperpolarized helium-3, which you can inhale and then enter an MRI machine in the absence of strong magnetic field and perform this imaging. And here on the right, you see a small miniature gyroscope that is based on the fact that those spins just maintain their direction in space, and when the whole platform rotates, you can sense this rotation. This relies, by the way, on the fact that the gyromagnetic ratio for the nuclear is much smaller than that of the electron, and so it's much, much less sensitive to magnetic fields, and it can maintain the direction. But of course, these are classical applications. And the reason we don't know about quantum applications with noble gas spins is because they are not accessible to light or to electromagnetic fields in the optical domain. The ground state spin has no transitions in the optical domain. And this is the challenge that we set out to tackle, and I will show you in this talk. Before we start, let me zoom out a bit and give you a bit of a broader overview about quantum optics with gases. So we already discussed spins with lifetimes of milliseconds and even seconds, and maybe in the future nuclear gas, nuclear spins. But there is another thing that one can choose to do, and this is to work with orbitals. So
Ofer, I'm sorry to interrupt, but I think the quality of the sound is not great. I don't know if there's anything you can do to
like move to headphones.
It's a little bit muffled.
Okay.
I mean, we can hear you, but it's a little bit muffled. So I don't know if you can change something, it would help.
Okay, that's right. So is the mic on?
Yeah, I think that might be better.
All right. Okay, so let me know. Do you hear the change?
I think so. Keep on talking. I think it is better. Yeah, thanks.
I'm not sure. I don't think this worked. Oh, you know what? Maybe. All right. So what I wanted to say is that one can now, instead of working with the superposition between two spin states, work with superposition between two different orbitals. For example, between this ground state orbital and some low-lying excited state, or even between a low-lying electron and a very highly excited state, which we call Rydberg state, where the principal quantum number is maybe 100 even. So because we are going to focus in this talk on these things, and since my group somehow covered the whole spectrum, let me give you a one-slide pitch on why sometimes people would not want to work with spins and actually work with orbitals. Okay. So here is a typical scheme for an orbital excitation. For example, we start with this ground state. We go up to the next orbit from S to P. Then we can go up and climb to the next orbit, maybe even D, and then another IR laser and excite a Rydberg atom. And you see here a nice looking Rydberg wave function, which I try to plot to scale compared to this ground state orbital. So it's really a big atom with a size of about a micron, and it has very large dipole moment. Now, all of these excitations are short-lived. I was alluding to long-lived spins, and you may ask yourself, why should I now move to very short-lived spins? And this is because actually they have quite some advantages. They could be much faster. They provide for much higher bandwidth, which may be important if you want to construct a quantum communication network. They introduce much less noise when you work with single photons. And this is because all of the control lasers have very different colors, and you can filter them out easily. And they are a stepping stone to Rydberg excitation, and so they could be used for atom-atom interactions. So the vision is to realize those very fast quantum optics processes and construct gates and sources and memories for single photons at room temperature that could be fast. And we just build now tools from several directions in order to realize this vision. So we constructed the first quantum memory that rely on orbital superpositions and excitation. It turned out to be quite a good memory because it has very low noise and it can have very high efficiency when you want to synchronize short photons. One thing that makes these excitations hard, the fact that you work with different colors means that you are very susceptible to Doppler broadening. And we developed schemes to use light in order to counteract Doppler broadening. And you see here an example how by introducing some compensating laser fields, we can take a broadened spectrum and narrow it and make it higher, and by that retrieve the properties of a medium where the atoms do not move, stand still. And we tailor our own single photon source. And we are developing this platform of a thin fiber through which light propagates. And because this fiber is very, very thin, the light actually, 99% of the light propagates outside of the fiber, it can interact with atoms. And the vision is to kind of put all of these components, really all four, together and build fast gates that are at room temperature based on Rydberg excitations. Okay, so that's it. That's all for the introduction and the starters, and now we are going for the main dish. And this is to bring noble gas spins into the light. This work is done in collaboration with the Quantum Optics Lab in Rafael, and particularly by these three excellent young researchers. Or Katz, who also initiated the study, he just graduated and is now moving on for a postdoc with Chris Monroe in the United States. And Roy Shacham was a PhD student, and Or Tal, who is a master's student, and they now continue this work. And now, okay, so what is the goal? The goal is to take the electric field, the light, and to couple it to noble gas spins. I mark this as SB. And since they do not couple, we're going to introduce some mediator between them, which would be the alkali atoms. So there would be also an alkali spin player. Now, light couples to the alkali through spin-orbit coupling, this we already discussed. And the alkali spins coupled to the noble gas spins by spin exchange collisions, which we will get to know now. Now, these mixtures of noble gas spins and alkali spins, they are not a new things. In fact, they have been here for quite some time and have been used for several applications. People mix alkali spins with noble gases in order to initialize the noble gas spins, to put polarization into it, to hyperpolarize the noble gas spins, and also to probe, to use the alkali atoms to probe the noble gas spins. Now, these two rely on spin exchange collisions. Here is how collisions look like. The two spins approach one another, and eventually they get out of this collision. And during this collision, there is some small precession, mutual precession that they do around each other. I say small, so this phi that characterizes the angle of precession can be very small, but it can actually be also very, very large. Here are some examples from our lab. This is our filling station. This is how the cell look like when it is filled. You see here results for a mixture of cesium with rubidium. So we use the rubidium to pump the cesium, and then we give the cesium a small kick, and we monitor the precession of the cesium atoms using the rubidium as a magnetometer, as a probe. And we have lifetimes on the order of half a minute. And this is the data that you saw already in a different form. This is the helium-3 initialized and measured by the potassium atoms, and it exhibits a coherence time of 2 hours. So these weak collisions, they function well to do these processes. Initialization, for example, so we use light, we pump the alkali, the potassium or the rubidium spins overnight, actually. And collisions, those weak collisions of potassium with helium or rubidium with xenon gradually transfer this angular momentum to the noble gas and pump them. And this is called ZIO, spin exchange optical pump. And as I already told you, alkali atoms can be very good magnetometers, so we can use them in order to probe the total magnetization of the noble gas. But this is not now what we want to do with those collisions. We now want something much more from them. We want them somehow to generate a strong coupling, an efficient coupling that is controllable and bidirectional, so that would be coherent and reversible between the two spins of the gases, between the collective spins of the noble gas and the alkali atoms. So this is a much harder requirement, and there are 3 challenges that I could kind of define to get this goal. First and foremost, I would say the most conceptually not obvious is to convince ourselves that those collisions can transfer quantum correlations, non-classical correlations, that despite the fact that they are weak and random, different collision time of different pairs colliding with different strength and each and every time, they could mediate quantum correlations. That's one challenge. Another challenge is the fact that they are very weak. In order for this exchange to occur, the electron spin from the alkali atom penetrates the nuclear spin of the noble gas atom, and they perform some very weak precession due to the Fermi contact term, due to hyperfine interaction. And this is on the order of 10 to the minus 5 per collision, so very weak. So we need to handle that, which also means we need to work with very high densities, so that collision rate are high, so collisions are frequent, but at high densities, we are prone to another problem, which is the collisions between the alkali atoms themselves. Now, these collisions are actually strong. They are due to the Coulomb exchange between the 2 electrons, and this could get to thousands of radians per collision, and they usually cause decoherence. So we need also to deal with that. And we will now talk about each of these challenges one by one. And let me start with this one, as this is the most conceptually simple because it also only has one species in it. So why do spin exchange collisions cause relaxation, and how do we circumvent that? In order to understand that, let me show you again how a collision looks like. Here you go. So what you saw in here are 2 atoms that collide. Each one has an electron spin and a nuclear spin. But in fact, it's only the electron spins that overlap and collide. And at this point, let me already tell you that if there was only the electron spin, in the absence of the nuclear spins, these collisions will not cause any relaxation. The relaxation is only due to the presence of the nuclear spin. And the reason is that if there were only electron spins, and because these electron spins, these atoms are indistinguishable, they are identical particles, and we address all of them in a symmetric way, all of the collisions between 2 electron spins would be a triplet combination, a triplet collision. So the atoms would climb the potential landscape during the collision and would then, climb down and get away. They will acquire some phase, a random phase, but this phase is global. It's not a relative phase between anything. As a global phase, it does not cause any relaxation. What the nuclear spin does, it introduces an electronic singlet component into the collision. That is, the correlations that pre-exist between the electron and the nuclear introduce a singlet component. So then when the collision occurs, each of the atoms enter in a superposition of triplet and singlet, and then acquire a relative random phase. And the relative random phase means that they dephase and they relax. And because of this process, spin exchange collision in our community is a synonym for relaxation. In fact, and it's for a good reason, because if you look back, you see that all of the experiments in quantum optics done in the past were eventually limited by spin exchange. And you see here examples from Harvard, from Copenhagen, and from this is data from my time at the Technion. These are all limited by spin exchange relaxation. And the reason these are limited by spin exchange relaxation is because they had correlations between the nuclear spin and the electron spin. And this is because they worked with one of these two processes. So this, what you see in here is the structure, the level structure of the cesium atom. I'm sorry, this is a bit technical, but what you need to take from this is, each and every column in here is a different spin angular momentum. And so this process changes the spin by 2 quanta of angular momentum, and this process changes it by 0 quanta. Now, as you know, an electron can only change by 1 quanta, which means that this process and this process both change also the nuclear spin. They involve the nuclear spin as well as they involve the electron spin. And so they generate correlations between the electron and the nuclear spins. And these are the correlations that then decohere when the atoms collide. And a while ago, what we realized is that if we instead use this particular simple looking scheme, you just pump all the atoms to a maximally polarized state, and you perform this transfer with the change of 1 quanta of angular momentum, then you generate no correlations between the electron and the nuclear spin, and you are free from spin exchange. So there are several ways you can understand that if you really want to. One is that you can just calculate this operator, how it relates to the triplet operator, and you just can see that it commutes. So if you start with a triplet, which is this stretch state, you end up in a triplet, so you never leave the triplet subspace. I can show you just kind of schematically. You start with both pins pointing up, and you either change the nuclear spin or you change the electron spin, but you never change both. And so all collisions possible in this scenario are triplet-triplet collisions. So we end up with a scheme that does not generate any singlet and therefore is not prone to relaxation. And here I must emphasize that this is not just 2 states, but it's a 2-state manifold. It's an SU2, it's a qubit. And so we can imprint a qubit onto this subspace. It's a decoherence-free subspace. Let me show you the experiments that shows that. So I'm showing you here a light storage experiment where we, I didn't talk about how light storage is done, so I won't detail this much. I'll tell you that we send a weak signal field, this is this laser, and we turn off a strong control field so that then we map the signal field onto a spin state of the atoms. We can then wait, and at a later time we can retrieve. This is akin to a Ramsey sequence, and of course it is sensitive to the lifetime of the spin. This is the memory time. And what you see in here is how we retrieve signals. These are different experiments, even after 1 second of storage time. So this is really 2 orders of magnitude more than other implementations in hot atoms. And this relies on this delta M equals 1 scheme. We can perform a reference experiment. This is the lifetime versus the atomic density or the collision rate, where we compare our scheme to a standard scheme with delta M equals 2. And you see that in the standard scheme, as we increase the collision rate, atomic density, the lifetime goes down, whereas in our scheme, it is completely insensitive to collisions. So we somehow won and took a spin shift relaxation out of the equation. One thing that we can do in this experiment, instead of retrieving the light, we can stop in the middle and probe the spins, see how the spins look like. And this is how they look like. So what you see in here are the state of the photons before we store and the state of the spins after we store. And each and every point on this circle is a single experiment. See many experiments in here. And what you see is that a point on the Poincare sphere is mapped onto a point on the Bloch sphere of the atoms. circles mapped onto things that look almost like circles, ellipses. Now, this is actually a very simple geometric interpretation for the state that we work with. We are working with just the orientation of the atomic spins. This is a kind of by luck in some sense. This is because the moment delta m equals 1 is pertained to the orientation moment of the spin. This is as opposed to delta m equals 0, delta m equals 2, which are much harder to recognize geometrically. And this gives you another intuition for why this is resistant to spin exchange, because if you just change the orientation of the spins, you take the spins in the vapor and you just change the orientation, then when they collide, there is no spin to exchange. They are already in pointing to the same direction. And this is why the orientation moment is the moment that one wants to work with, because this is the one that is resistant to spin exchange. Okay, up until now. So before I move on to the next challenge, I'll mention that this experiment was done with only the alkali spins in the cell. But now we're going to introduce noble gases, and which in general terms is a buffer gas. And one thing that is very well known for alkali atoms is that when you mix a dense buffer gas with them, you smear the structure of the excited states. So these states, the nice states that we used previously in order to generate this nice linkage pattern, they are no longer resolved. And specifically, we have this our process that we use to map photon state to orientation, but this is now accompanied by this competing process. And these two actually destructively interfere, and so we can no longer do what we did before. So what we had to do when we moved on to work with buffer gases is to develop a new linkage that allows us to access the orientation. And we did so. We don't yet have a name for that. So let's call it for now nonlinear void effect. Still think of a good name. It relies on some polarization modulation and some polarization demodulation at the end. But what it does is it allows us now to, again, access the orientation moment of the spins. And I can show you a very preliminary result with this scheme. So you see here spectroscopy that is done on a gas with a lot of buffer gas. So this is with 3 atmospheres of buffer gas. And again, we access the spin exchange resistant subspace. And this shows in the very, very narrow spectrum that we measure. This is done again at room temperature, and it's a 20 Hertz optical line at room temperature. So we believe that this mechanism, this way of interacting with the orientation of the spin, which we still don't have a name for, would actually be a huge enabler to the field when people now will work with high buffer gas cells.
So can I ask you what's
Daniel, we don't hear you. I don't hear you. Maybe.
Can I ask you what's the idea behind the trick?
No, wait. Can you play?
The question was, can you say something about what's the idea behind this trick that you use to do this?
Maybe the feeling I could give you is that so we generate circular polarization. The modulation is between circular polarization and linear polarization. Everything is done off resonantly so it's a Raman transition that is very far detuned. And so everything we need to think of as in this coupling is dispersive coupling, okay, off-resonant coupling. So what circular polarization does in dispersive coupling mode is it generates, it's a light shift, it's a vectorial light shift, and it rotates the atomic spins. So this gives us the orientation, okay, the rotation. But then this everything is done in a magnetic field, so the spins, the alkali spins in this case, they keep on processing. So after a quarter of a period, they now have a component that is aimed with the direction of the light field propagation. So at this point, and we tune this exactly, the polarization becomes linear. This is this polarization, and a linear polarization with a spin that points along the direction of propagation is akin to a Faraday effect, Faraday Hamiltonian that rotates. Okay, it's a circular dichroism, and it rotates the the polarization, the linear polarization. So we alternate between circular and linear polarization. And for the spins, this alternate between tilting them and getting back some back action. And this is why this is a bi-directional coupling. Okay? I will show more results with this scheme later.
Okay, thanks.
Okay, so we solved challenge number 1, and we got to the point where collisions between alkali atoms no longer causes relaxation, and we are able to get the relaxation of the alkali atoms even at very, very dense scenarios when they collide frequently and there is a lot of buffer gas to the order of 10 Hertz. Okay, next challenge is how do we make weak collisions couple the two spins so efficiently? And to understand this, we need to first understand what exactly we want to do. So here again, I remind you, we start all the experiments by pumping the atoms, the alkali spins and the noble gas spins to one direction. And I'm showing you here data. This is pumping overnight, so this happens at night. Of course, the alkali spins are polarized immediately when we turn on the light, but the noble gas spins gradually polarize due to accumulated of these very, very weak collisions until at the end of the, when we come in the morning, we have about 30%, even more polarization for the noble gas, okay? Which sounds not a lot, but it's still actually a record. So the state that we start with, our ground state, is simply the state with all the spins pointing up, or many of the spins pointing up. Of course, it has this uncertainty around it. This is the classical pumped state. And we think about, again, our collective state, which is the sum of all spins. This is the SZ component of this spin. And the uncertainty has the size of the square root of the number of atoms. The ground state is simply all the spins pointing up. And now the first excited state of this spin would be the state where we have one spin pointing down. We don't know which, the superposition, it's a collective state. And in order to get that, we operate with the operator S minus, simply the ladder operator, S6 minus ISY on the ground state. And we generate one excitation. And we can do this again. And then we generate two excitations. This is the state 2. Okay. So what we do at this point is we recall that the longitudinal operator, SZ, is actually macroscopically populated by n atoms. And we replace it by a C number, by a classical number. This is called, so this is done in other field, but in our field, this is called the Holstein-Primakov approximation. And when we do that, we map the operators S minus and S plus onto bosonic collective excitation. So of course, this assumes that n is large and the excitations are small. And we get these harmonic oscillator operators, which take and remove excitations from the ensemble. These operators, these collective bosonic operators, these are the operators we want to couple between the two spins. Okay. One more intuition I can give you for these operators is that if you look at the mean field, if you take the expectation value of them, displacement operators, you simply get the expectation value of the total spin, which is just the orientation of the spin. So if you remember, orientation is something that we like now so much because it is insensitive to spin exchange relaxation, and it's a good thing to work with. So this orientation, again, is the thing we want to couple, which is the transverse excitation, quantum transverse excitation of the whole spin. So longitudinal excitation, we are now took as a classical number, and we only care about quantum transverse excitation of this spin. These are the ones we want to couple. We are going to couple them with stochastic collision. Actually, calculating this process is not very hard if you want to do this on the classical level for the mean field, for the mean spin. The expectation value of A and the expectation value of B, when you mix them up together, simply sums up to a dynamics of mutual precession around each other. You need to sum over many collisions that happen in random times, random pairs colliding with random strength. You know some statistics about these collisions. You know the average strength of the collision, phi, maybe higher moments like phi squared. And if you do all that, you get just mutual precession of the total spins around each other, which maybe makes sense because the accumulation of many, many small precessions. If I cast this to the language of our bosonic excitations, I get this, just simple two harmonic coupled oscillators. They have the basic form that we all know and love. There is the decay of the spin gamma. I only wrote the decay of the alkali atoms. The noble gas atoms, I assume that they do not decay at all, but they have a 2-hour lifetime. They have the frequency mismatch, which I can control. This is the mismatch between the precession frequency in the magnetic field. And since the magnetic field, the external magnetic field, acts very differently on electron spins and nuclear spin, there is a factor of many hundreds, even 1,000 between them. I can tune delta externally very quickly. And they are coupled by J, which is the collective exchange rate. This is due to accumulation of many, many collisions. And it is nice to see the expression. So this is the collision cross-section and the rate. And there is a prefactor, which is the square root of the densities and the polarization degree of each of the ensembles. And the fact that there is a square root in here and it's not linear shows you that this is a collective term. This couples collective quantum excitations. And if now we want to make this coupling efficient, we need J to be much larger than gamma and delta, which means we want to make those as small as possible, and we want to make J as large as possible by cranking up the densities and the polarization degrees of both species. And this is what we did in this experiment. So again, we have a cell, we pump all the atoms up. These are the data, close to 10 to the 13 helium atoms. Oh, sorry, this is really a mistake. This is 10 to the 20, okay? 10 to the 20 helium atoms, 4 10 to the 15 potassium atoms inside about 10 centimeters square. And we begin the experiment by turning on a short magnetic pulse of transverse magnetic field that tilts mostly the alkali spins to one direction. So we give it a very small tilt on the order of 1 degree. This is not a quantum experiment. There are many, many spins that are flipped with this 1 degree tilt. It's about 10 to the 14 spins that are flipped. And then we monitor the dynamics. And what you see in here is the data for the first 20 milliseconds, showing the periodic exchange back and forth of the excitations from the alkali until it is depleted completely, and to the noble gas and back, and again to the noble gas and the alkali. And you see from these multiple excitations and also from these numbers comparing J to gamma that we indeed reached the strong coupling regime, where we can exchange excitations between the gases without losing due to decoherence. We can scan delta, this parameter, and measure the spectrum of this system. And again, you see here 2 branches, and at resonance, this very wide gap compared to the width of the branches, which again is an evidence for the strong coupling regime. And the fact that we can actually tune delta in situ by the magnetic field means that we can turn on this interaction for a specific time, say a pi pulse, and stop, and then detune them away to the point where they are decoupled. And this means that we store the excitation that were on the alkali and the noble gas. And then at a later time, we can turn them on again and retrieve. That is the future idea. All right, so we are done with the 2 experimental challenges, and we are left with the conceptual challenge. Is this quantum? And for this, I don't yet have an experiment to show you, but I can show you analytic and numerical results that indicate that it is indeed quantum. For the analytical, this is actually an effort, a long time effort for the last 6 years or so, where we constructed gradually models to describe the dynamics of these quantum spins, which are spatial distributions of the spin in space and time under the different processes that happen in our system, spatial diffusion and spin exchange collisions and wall collisions, and collision, of course, among themselves and between these two. All of these models are fully quantum. They are stochastic model. So we use the Heisenberg-Bloch-Langevin formalism. And they include all the associated quantum noise operators that result from these processes. And one nice thing is that they are numerically tractable. So now one can use them, for example, if you want to measure how the squeeze spin state that you generate in one side of the cell is expanding and decaying over time, which is relevant to several experimental efforts that are done worldwide. And for us, in this context now, the most important thing that these models predict is that indeed the accumulation of all of the collisions accumulate to the collective exchange, not only between the mean field, but actually between the quantum operators of these two spins. So the same equations you saw before, you saw that for the mean field. We believe it is actually valid also on the quantum level, of course, with the accompanied appropriate quantum noise operators. So this is an analytic result that we hope is correct. Let me show you maybe a numerical result to give you an intuition again how accumulation of stochastic collisions can mediate quantum correlations. And what I'll show you is a simple simulation done in MATLAB, a few tens of code lines, maybe hundreds, where we take it's a full many-body simulation, so it has no approximation in this sense. We have follow 10,000 noble gas spins and 100 alkali spins, and we initialize the simulation with one spin flip. And I compare for you two cases. On the left, I choose one of the spins, specifically spin number I, and I flip it, the alkali spin I. And on the right, I do not choose anyone. I actually put the single excitation in a superposition of all spins, which is the collective singly excited state. So I operate with A double. And when I run the simulation, so random collision with random strength of random pairs at random times, I get these two behaviors, which at the beginning look the same. The alkali spin is simply lost to the bath of 10,000 nuclear spins. But if I continue the simulation for longer, for more time steps, I see a striking difference between these two. When I just flipped one of the alkali spins at the beginning, it was just lost to the bath of noble gas. But when I generated this collective state, this one was actually much faster transmitted to the noble gas, and then at some point reversed. This is just coherent oscillations, and got back, and lost again, and got back. So you see that even in this numerical simulation that is stochastic by nature, we get these coherent oscillations between the collective excitation of the alkali and the collective excitation of the noble gas. And in fact, the fact that it is coherent relies on the fact that the collisions are weak. The decay that we're seeing here is not because we introduced decay into the simulation. There was no homogeneous decay explicitly by hand put in the simulation. All of this decay comes from the fact that the collisions are not very, very weak in here, but rather they are a bit strong. And if we make the collision even weaker, we would get more oscillations per relaxation time. This is a bit somewhat akin to motional narrowing, decay narrowing. So that's it. Before I conclude, let me show you one very promising experimental result that we recently got. So the way you would naively think about an experiment is you would pump all the alkali atoms, alkali spins. You would then at some point imprint an excitation on them, maybe using light, and then you will turn on the interaction by tuning the magnetic field to resonance. You will map this spin state onto the noble gas spins. Then you can wait an hour, drink a cup of coffee, come back, pump the alkali again, turn on the interaction, read out the excitation to the alkali spins, and then read them out using it. That would be the naive approach. The less naive approach would be to do all of these things together, to couple the light during the spin exchange interaction so that everything happens together. And this is what we did in this experiment. So the system is the same. It uses this process that I talked about with polarization modulation and demodulation. So here is the coupling and of the light to the alkali atoms, and here is the coupling of the alkali atoms to the helium atoms. And we play one trick. We turn on a magnetic field that detunes the potassium spins away from resonance. So the potassium spins are never really excited. They are only virtually flipped. The only spins that are actually flipped are the helium atoms, and the potassium acts as a virtual mediator. similar to a Raman transition where the excited state acts as a mediator. So we turn all of these interactions on and we measure the response of the atoms and the light. So first, you can see what the light sees. So this is the effect of the helium on the light, and we tune through the resonance, and you see a very sharp absorption of the light. This is 50% absorption of the light by the helium atoms. And the striking feature here, of course, is the line width. This is done in room temperature, and this is an optical spectrum. We scan the frequency of the optical probe, and we get a 10 millihertz line width at room temperature of moving atom. And it's coherent, and it's accompanied by the what you would expect from the coherent resonance. This is the accumulated phase shift. The line here is a model that encompasses this process with the helium spins and the alkali spins. In fact, we can even detune the alkali further away and get this down to 5 millihertz. So this is still governed by the alkali relaxation. In the future experiment, we can detune even further more and get even narrower line width. This is, by the way, akin to a minute long lifetime. So we now couple light to a spin with a minute long lifetime at room temperature. And lastly, I can show you what the spins do to the noble gas atoms. And what we do in here, we turn on the light for a short time, and then we probe the noble gas atoms. And you see that when we are with the light on resonance, the noble gas atoms start to process. This is data, and you see a precession of the noble gas atoms that were set by the set out that were stimulated by the photons. So this is our bidirectional interface in which photons can excite noble gas spins, and the noble gas spins can affect back the light. That's it. Where are we taking this? So we put out two proposals for quantum experiments. Everything I showed you in the experiment so far is classical experiments. One is to perform light storage on noble gas spins. So this is in these two regimes of doing this sequentially or in parallel with either very fast pulses or slow, long pulses. Another proposal is to entangle two noble gas spins. This is, in fact, the one we are going to start with. So this is the one we are going to pursue in the next couple of years. Here, the light passes through two cells of noble gas, so that at the end, it measures the total spins of the noble gas atoms, but it does not measure the difference. So in that, it would entangle the two spins. It would put them into this two-mode squeeze state. And there are predictions that we did of how much squeezing we can produce. And I remind you, this squeezing should or entanglement should persist for hours or maybe more in a future system at room temperature. So this should be a very, very long-lived entanglement. I will conclude with the photos of the whole group, past members and current members, and highlight the people working on the project I've shown you. And thank you for listening.
Thank you. So now we have time for a few questions. If anybody has a question, just open your microphone and ask. Okay, maybe I'll ask a question. Just so I guess I didn't. So I don't know if I understood fully how these, once you have the system, of alkali atoms and noble gas, strongly coupled. So you still manage to maintain very long coherence times. So what controls the coherence time then of the coupled system?
So we can differentiate between the two. If they are not coupled by this spin exchange collision, if they are not coupled resonantly, so for example, if the magnetic field is not tuned exactly to make the two precession frequencies the same, then they are decoupled ensemble. And then different processes cause different relaxations. For the noble gas spins, we are currently probably limited by inhomogeneous magnetic fields, partially due to inhomogeneous magnetic field that we ourselves turn on. So this is the external field around which our helium atoms precess for 2 hours. If there is some spatial inhomogeneity and fluctuations, temporal fluctuations of the current that runs, and there would be decoherence. And partially, the inhomogeneous magnetic field come from the fact that the atoms, they do not only occupy the spherical cell, but they also sometimes enter a small cone shape, triangular shaped stem. This is a remnant of the stem that was used to put them in to begin with. Now, you may know that if you take a sphere of identical dipoles, they produce a homogeneous magnetic field. But if you do anything else, not a sphere, but a sphere with a perturbation, then around the perturbation, the magnetic field will not be uniform. So even that limits our lifetime. To give you a feeling, at the beginning, we suffered from a shorter lifetime than these 2 hours. And the way to get to 2 hours was to introduce enough potassium into the cell that would fill up this cone with metallic potassium. And in fact, we now currently heat and cool this stem in order to make the potassium exactly cover the full cone, and only then we get to 2 hours.
Okay, are there other questions? Okay, well, if there aren't, let's thank Ofer for this talk. And
thank you for the invitation, Daniel.
Thanks.